and I'll start recording. We're on page 59 of the lecture notes. Page 59, section 6, the problem of serial correlation. And what we're talking about here is another example of a violation of the classical assumptions. Remember a few lectures ago I told you what the 6 classical assumptions were. These are the assumptions that are necessary for ordinary least squares to be the best linear unbiased estimator. And there were 6 of those assumptions, and each of those assumptions can be violated. So for example, last week we considered multicollinearity. Perfect multicollinearity is an example of a violation. Heteroscedasticity is a violation. Here's the next one, serial correlation. This is a violation of one of the classical assumptions. Serial correlation, sometimes known as autocorrelation, is the situation in which there is a pattern over time in the error term UT. Pattern over time. Now, it's a bit like heteroscedasticity, except remember heteroscedasticity is fanning out. Like that. This was last week's lecture, page 50 of the lecture notes. There was a pattern in the error term, but this is a cross-sectional pattern, because heteroscedasticity is a problem that usually arises in a cross-section context. We have data on households or workers, in this case, earnings against years of experience, and there was fanning out. This is a cross-section example. Now, there is a pattern in the error term, and the pattern is fanning out. And any sort of pattern in the error term indicates a problem with the model. So that was heteroscedasticity. Here we're talking about a different sort of pattern in the error term. We're talking about a pattern over time. So consider the consumption function. This is a time series model. Consumption in time t depends on income in time t. Now this is a macroeconomic model. Aggregate consumption, personal disposable income. And yeah, the diagram that's relevant here is basically this. It's a consumption function. Consumption against income. And the thing we're trying to estimate is the thing that we call the consumption function, and it has intercept beta 1 and slope beta 2. And we've used this example a few times. The intercept in this model is what's known as autonomous expenditure in macroeconomics. And the slope in this model is the slope of a consumption function is what's known as the marginal propensity to consume. Or MPC, an important quantity in macroeconomic models. So this is the consumption function. Now the thing is, these two variables, they tend to rise over time because of economic growth. Aggregate consumption is rising over time, aggregate income is rising over time. So over time, we will tend to climb up the consumption function. The question is, how do we climb up? Is it random? Well, serial correlation is the following sort of pattern in the error term. If we have a string of positive errors followed by a string of negative errors followed by a string of positive errors, then that's what's called positive serial correlation. Now, I'm making it a bit obvious here. The pattern would not look this perfect, but we would see a pattern like this. We're likely to see a pattern like this if we're working with macroeconomic data. Aggregate consumption tends to follow boom-bust cycles. This is the dependent variable in this model, boom-bust cycles. This means there will be boom stretches, such as here, in which consumption is above the regression line, and the error term is positive. See, positive error, positive error, positive error, followed by bust stretches. So we're calling this a boom, and we're calling this a bust, and then we're calling this another boom again. Bus stretches in which consumption is below the regression line and the error term is negative. So we have negative errors here and here. Right, this means that if the error term is high and positive in period t, ut, error term ut, if that's ut and that's high and positive, then that's because we're in the middle of the boom. So ut plus 1, which is there, will also be high and positive, because we expect the boom to last for several time periods. If ut is high and negative, for example here, then we expect ut plus 1 to be high and negative as well, since we expect a bust or a slump to last for several time periods. Another way of saying this is that the error terms in 2 consecutive time periods are positively correlated, because high is followed by high, and high negative is followed by high negative. Another way of saying this is that the error terms in 2 consecutive time periods are positively correlated. Yet another way of saying this is that we have positive serial correlation or positive autocorrelation. So this is the sort of pattern we're talking about when we talk about serial correlation, and it's a pattern that we get when we're doing time series modeling, for example, macroeconomic modeling. Page 60, formalizing serial correlation. We assume that the error term is generated in the following way. See, the error term, remember, is this thing that's added on at the end of the regression equation, and it's essentially the vertical distance of a point from the true regression line. That's what we've been talking about. We're saying that ut has this pattern of a string of positive values followed by a string of negative values. How do we model that? We assume, this is page 60, we assume that the error term is generated in the following way. Ut is rho ut minus 1 plus epsilon t. Rho is a new parameter which takes the value between minus 1 and plus 1. Notice that when we say the absolute value of rho, this vertical lines, that means absolute value. If we say absolute value of rho less than 1, that's like saying rho is between minus 1 and plus 1. So it's just a fraction that's less than 1 in magnitude. That's what rho is. And we also have an error term, epsilon. This is a new error term. Obviously, u is an error term itself, but we've got a new error term, which we call epsilon. Right, if rho is positive, all right, 2 is known as a first order autoregressive process. Autoregressive just means the variable depends on its own previous values. That's what autoregressive means. First order means the variable depends on its last value, only on its last value. That's what makes it first order. If it depended on the previous 4 values, then it would be fourth order or second order. We'll consider those in a minute. If rho is positive, we have a situation of positive first order serial correlation. Rho is positive. That's if rho is positive, that means that ut and ut minus 1 are positively correlated. If rho is 0, then this term disappears and we are left with epsilon t. We have no serial correlation, because think of epsilon t as a well-behaved error term. If rho is negative, we have negative serial correlation. If rho is negative, then that means ut and ut minus 1 are negatively related. So it means if ut minus 1 was very high, then it means ut is going to be high and negative. Opposite sign. So what does negative serial correlation look like? Well, if that's our y variable, if our dependent variable is y and our explanatory variable is x, and the true regression line is this, then negative serial correlation looks like this. So we are zigzagging above and below the true regression line. See, like this, above, below, above, below, above, below. That's what negative serial correlation looks like. Now, this is quite unusual. Notice the difference. Positive serial correlation is what we considered on the last page, a string of positive errors followed by a string of negative errors. Negative serial correlation is not that. It's one positive followed by one negative followed by one positive. So we are constantly moving from one side to the other. And this sort of thing happens. It's a bit unusual. This is what you get when rho is negative. It's negative serial correlation. Now, it's unusual, but situations in which you see this are situations where people constantly make mistakes. Every period they produce too much or too little, or every period they charge a price that's too high or too little. One example of that, which I haven't got time to go into detail on, is models of agricultural production. Use the pen. Models of, this is EG, models of agricultural production. Now, there is a famous model in economics called the cobweb model. In which agricultural producers or farmers base their production decision on the price. Now, the price is current. Farmers observe the price this season. And if that price is very good, if that price is very high, they produce a lot next season. You see, the production decision is made 1 year ahead. So if the price is very high, farmers decide to produce a lot, and as a result of them all producing a lot, the price is low in the following period. And when the price is low, farmers produce a little. So the cobweb model is a situation where we have, if this is agricultural production, we have agricultural production is too high one period, and in the next period it's too low, and then the next period it's too high, and so on. So that's one example of a situation where you might see negative serial correlation, but it's usually positive serial correlation, which is the example I showed you on the last page. Second order serial correlation looks like this. The error term in T depends on the error term in T minus 1 and the error term in T minus 2. And there's a separate error term there. This epsilon T, think of that as a well-behaved error term. That one doesn't have serial correlation in it. When working with quarterly data, there are good reasons to expect fourth order serial correlation. So yes, if you're working with quarterly data, then you've got 4 observations per year. So you might expect the quarter 1, well, what are we in now? We're in quarter 4. Quarter 4 of 2021 is probably going to be related closely to quarter 4 of 2020, the previous year's quarter 4. So that's why we might expect fourth order serial correlation when we're working with quarterly data. Well, when you're working with annual data, you can get fourth order serial correlation. It's a thing we need to test for. So this is what fourth order serial correlation looks like. There are 4 row parameters. We wish to know if serial correlation exists and what order it has. A problem is that we do not know the values of the errors UT. However, we do know the values of something similar, namely the residuals UT hat. Okay, remember the thing we're talking about here, the line we're talking about here is the true regression line. So the distances of points from the true regression line, that's what we call the error terms. Once we've estimated the model and we've got a fitted line here, then we have the residuals, and the residuals are, we observe the residuals. We've got the numbers for the residuals, and the residuals are closely related to the errors. So if we want to examine the errors in a model, as we want to do here, then the obvious thing to use is the residuals. So that's the point that we're making here. We do know the values of something similar, namely the residuals u hat t. So we could replace ut by u hat t in 2. This is first order serial correlation. So if we put u hat there, u hat t, and u hat t minus 1 there, then we have something like a regression. We can do a regression of residual on lagged residual. Well, this is it. This is a regression. We could run the regression 5 without an intercept. Notice there's no intercept in this equation. Obtaining an estimate of rho, and the estimate of rho would be, this is the slope estimate in simple regression. Remember, the formula for the slope in simple regression is sum x minus x bar y over sum x minus x bar squared. That's the general formula when you have a y and an x variable and you're doing a regression of y on x, then the formula for the slope is given by this. Okay, well, if we're doing a regression of residual on lagged residual, then the residual, the ut, the residual goes there, and the lagged residual goes there. But the thing is, residuals have mean 0. Okay, so there's going to be no mean. The mean's going to disappear. And that's essentially why the slope in this model is given by this formula here. Note that the first observation has been excluded from this regression. Yes, we're doing a sum from t going from 2 to n. Why are we excluding the first observation? That's because we're using a lag of something. If you use a lag of something, if you've got t minus 1 of something, then you lose the first observation. Because when t is 1, u hat t minus 1 doesn't exist. So whenever you've got lags in a model, you have to lose the first observation or the first observations depending on how many lags there are. We will see that a lot of times. So that's the answer. The first observation has been excluded. Why is this? That's because ut minus 1 hat appears in this model. That's why we lose the first observation. 61, page 61. We could then try to do a test of the null hypothesis that rho equals 0. That's no serial correlation, against the alternative hypothesis of rho positive. That's positive serial correlation. So what we're saying here is, here's a regression. We do this regression without an intercept, and then we test the hypothesis that rho is 0 or positive, and that's a test of serial correlation. Now there is a problem here. A straightforward t-test is inappropriate here. This is because the t-test statistic does not have a t-distribution under the null hypothesis. Why is that? Well, I'm not going to explain that. That's econometric theory, which we don't, which is beyond the scope of the module. But basically, with time series data, you always get into strange problems if you try to do a regression of a variable on its own lag. The theory that we normally use does not apply anymore. So as I just said, when we do a regression of ut hat on ut minus 1 hat, and we consider a t-test on the parameter rho, that t-test statistic will not have a t-distribution. So in other words, we can't do the t-test. Instead, we use the Broich-Godfrey test. To perform this test requires the following steps. Well, if you're in Stata, then you just have to use the B-Godfrey command, which is here at the bottom of the page. But for completeness, I'm explaining what the Broich-Godfrey test actually does. If you wanted to perform it yourself, you would use the following steps. You'd estimate the model of interest, y on x. This is the original model in which there's an error term, and you're interested to test whether the error term in this model has serial correlation. So you estimate this model. It might be consumption on income, or it might be something else. And it's a time series model. That's why we've got a T. And we store the residuals as UT hat. Then we generate UT minus 1 hat. That is, we generate the lag of the residual. And you can also generate the second lag, the third lag, the fourth lag, if you want to test for higher order serial correlation. Now, it's easy to generate lags. You just use the lag command, gen, what we call it, gen lag u hat equals lag is the command. That's how you generate a lag. You just use the lag command. We'll be doing this in seminars in this week. So the seminar on Friday of this week, we will be doing this. Generate the lags of the residuals. Now, the first values of the lags will be missing. This is quite important. They're missing values. For the purpose of this test, you replace these missing values with 0. Remember, residuals are 0 on average. They take positive values and negative values. They're 0 on average. So replacing residuals with 0 does not seem too serious a change. But when we're doing the Boyce-Godfrey test, that's just something that happens in the process of doing the test. I explained earlier why the first few values of the lags are missing. Because when you take a lag of a variable, you're essentially moving that variable down by a row. And every time you move it down, you're losing an observation at the top of the list. Okay, this will become clear when we're doing this in Stata. Then, number 4, run the following regression. And this is for a test of first order serial correlation. It's a regression of UT hat on the lag of UT hat and XT. That's for first order serial correlation. The important thing is we're including the X variable. Whatever the explanatory variable is in the model, we're including it here in the in this, what we call the auxiliary regression. And we're not going to do a t-test on rho. We're going to do something else, which I'll come to in a minute. That's for a test of first order serial correlation. If we want to do a fourth order serial correlation test, then we do a regression of residual on lagged, first lag, second lag, third lag, fourth lag, and also the X variable. The X variable is the explanatory variable in the original model. Now, at this point, we're not going to do a t-test or an f-test. We're going to do an nr squared test. Find the nr squared from the model of 4. This is 4. So whatever we did here, whether it was on 1 lag or 4 lags, we find the r squared from that model, and we multiply by n, which is the sample size used to estimate the model. nr squared. The result is the Boyce-Godfrey test statistic for testing serial correlation in the original model. And notice, as I stress, it's not a t-test or an f-test, it's an nr squared test. And how do we know if it's significant? Under the null hypothesis of no serial correlation in the model of 1, the test statistic has a chi-squared Q distribution. Now, I don't think we've seen the chi-squared distribution before, but it's a bit like the F distribution. Chi-squared distribution with Q degrees of freedom, where Q is the order of serial correlation being tested. So this is usually going to be chi-squared 1 because we're usually testing for first order serial correlation. You therefore need to compare the test statistic with the critical value, chi-squared Q 0.05, from chi-squared tables. Now, there's a formula sheet which you were given a few weeks ago. It contained the simple regression formula It contained critical values of the T distribution, critical values of the F distribution. And on the final page, we have critical values of the chi-squared distribution. And down the side, we have the degrees of freedom. And along the top, we have the alpha value. So as usual, well, the chi-squared is a bit like the F distribution. It's always positive. And if we're looking at the chi-squared 4, say, then we're looking in this row of the chi-squared table, and we've got some alphas. Usually we use alpha equals 0.05. That's the convention. So to get the tail area 0.05, we use the critical value 9.49. That's the number that we read from the table. And if our test statistic is to the right of 9.49, then you have evidence to reject the null hypothesis. The null hypothesis is no serial correlation. So if our test statistic is to the right of that, then you've got evidence of serial correlation. It's like that. Where does this chi-squared distribution come from? Well, you see, the F distribution is a bit like this, because the F distribution is for testing restrictions, joint restrictions, a number of restrictions. The number of restrictions being tested is the number you see here, DF1. That's the number of restrictions you're testing. DF2 is like the sample size. That's n minus k. Now, when the sample size is very large, we're here. When the sample size is very large, we're in the bottom row of the F distribution. Well, when the sample size is very large, the F distribution becomes the chi-squared distribution. Roughly speaking, it's not exactly that, but it's essentially that. When the sample size is large, we have the F, what do we call it? Q. It's a number of, no, we call it R usually, don't we? F R infinity. When the sample size is large, so infinity say, we have the F R infinity distribution. But this is when we're testing R restrictions. What I'm telling you now is that F R infinity is the same as almost the chi-squared R. So what I'm telling you right now is that the chi-squared distribution is a large sample version of the F distribution. In both cases, we're testing R restrictions. When the sample size is very large, the F distribution becomes the chi-squared. And that's why we only need 1 degrees of freedom when we're using the chi-squared. That's why for the F distribution, we need a whole table for alpha equals 0.05. For the chi-squared distribution, we've got a different column for each alpha. So in a sense, it's easier to do a chi-squared test because there's only 1 degree of freedom. So that was just showing you where the chi-squared table is and how to use it. But, you know, as always, Stata does this test for us. When Stata does it for us, we don't need to worry about the tables because Stata gives us the test statistic and it gives us a p-value. But I think it's nice to know what this process is so that you can verify that that is what's actually happening when you use this Stata command. There is a Stata command, bgodfrey, lags 1, 2, 3, 4, or just lags 1, which performs all of these steps in one go and tests for first, second, third, and fourth. If you put all those numbers in, then you'll get a test of all 4. You'll get all 4 tests of serial correlation. In workshop 7, question 1, we verify that the 2 methods give the same answer. It's a consumption function. It's a regression of C on Y. This is the workshop that we're going to do this Friday. So the consumption function looks like this. That number that you see there is the estimate of autonomous expenditure. That number that you see there, which is the slope associated with Y, which is income, national income, that number there is the marginal propensity to consume. So this is estimates of the parameters of a consumption function. And then having estimated this consumption function, we can do the Boyce-Godfrey test for serial correlation. So exactly as I've just mentioned in the lecture notes, V Godfrey, comma, lags 1, 2, 3, 4, that gives us 4 different tests. For first order, second order, third order, fourth order. And it's called the Boyce-Godfrey LM test for autocorrelation. Now, the number that I told you was when you do an auxiliary regression and you get an NR squared, the NR squared that you get is the number that you see here in this column. N times the R squared gives you whatever number you see here. The degrees of freedom for the chi-squared test are the number that you see here. Obviously, if you're testing first order, it's 1 degree of freedom. If you're testing fourth order, it's 4 degrees of freedom. And then, most importantly, I guess, the p-value is what you see here. The p-value is the number you see in the final column. And as always, if a p-value is less than 0.05, then you have significance. So we have evidence here, we have evidence of second order serial correlation. We have evidence of third order, we have evidence of third order serial correlation. And we have, because they're both less than 0.05, and we have strong evidence of first order. Notice we only have mild evidence of fourth order. So that's how we conclude the results from the Boyce-Godfrey test. That's how we interpret the results. If we're testing for first order, Boyce-Godfrey test statistic is 6.64, and we want to compare it to a chi-squared 1 from tables. Well, yes, you can do this if you want. Chi-squared 1, the critical value is 3.84. Since the test statistic of 6.64 is higher than 3.84, we have evidence of first order serial correlation. Note also that the p-value is less than 0.01, so the evidence is strong. Note also that there's evidence of second order and third order serial correlation. If you want to compare that number to tables, then obviously it's a chi-squared 2. Chi-squared 2, 0.05. 5.99 is the critical value. That number there is greater than 5.99, so we have evidence of second order serial correlation. And the p-value is worked out by Statter. I mean, you could work out the p-value approximately, couldn't you? If your test statistic is 7.28 and it's a chi-squared 2, we're looking in this row here, 7.28. There's 7.38. So if we imagine 7.28 is here, what would the alpha be to give us 7.28? Well, alpha would be bigger than 0.025, but less than 0.05 and closer to 0.025, and that's the number that you see here. It's 0.0262. That number there. So all I'm doing here is I'm explaining how you could, if you wanted to, work out the p-value roughly, not exactly, but using the information that you have in this table of the chi-squared distribution. Note also that there is evidence of second order and third order serial correlation, but only mild evidence of fourth order, because that p-value there is bigger than 0.05. I guess you're all getting used to this, how to interpret p-values, because you've finished the take-home assignment. Well, I think the students who are here have finished the take-home assignment. The ones who are not here are still working on it. Okay, the chi-square distribution is closely related to the F distribution. This is what I was telling you about earlier. When I showed you the F distribution, I said, remember the F distribution. I said, look in the second degrees of freedom is like the sample size. When the sample size is large, we're looking in the last row. The last row of the F distribution is like the chi-squared distribution, because when the sample size is very large, the F distribution becomes the chi-squared distribution. Remember, the F distribution had 2 degrees of freedom. Number of restrictions being tested, and n minus k, where n is the sample size. If the sample is large, that is, if n is roughly infinity, then f r n minus k becomes chi-squared r. Hence, we can think of the chi-squared distribution as a large sample, or asymptotic. That's a good word. Asymptotic, that means large sample. It means when the sample becomes large. Don't mix this word up with asymptomatic. That's another word we hear a lot at the moment. Different word. Asymptotic means n is large. So it's an asymptotic version of the F distribution. F distribution is what we call a small sample test, or an exact test, because the F distribution is a small sample or exact distribution. That's because one of the degrees of freedom is n minus k, so the F distribution can be applied to any sample size. The chi-squared distribution is applied when the sample size is large. Right, page 63. The Boyce-Godfrey test is an example of an asymptotic test. That is a test that is valid provided the sample size is large. This is why the distribution of the test statistic under the null is chi-squared. Well, important question, why is serial correlation a problem? All I've told you so far is how you test for serial correlation, how you would detect it. And the answer, to detect it, you use the Boyce-Godfrey test in the way that I've just described. So that would tell you whether you have this problem. But why is it a problem? This is important. Any pattern of the error term implies that there's some feature of the data which we're not taking account of in estimation of the model. This means that the model that we're using gives less precision than would a different method which takes account of this feature. Now, the argument being used here is the same as the one we used in the case of heteroscedasticity. There was a pattern there. If we took the fanning out pattern, if we took account of that pattern, we get a better estimator. We get a more precise estimator. Ordinary least squares takes no account of these patterns. So this is the point. This is why ordinary least squares is no longer the best estimator when you have any sort of pattern, including autocorrelation. Autocorrelation, serial correlation, remember they're the same thing. Serial correlation per se does not lead to any bias in estimation, although see point 3 below. More seriously, the formulae that we use to compute standard errors when we use OLS are built on the assumption of no serial correlation. So again, this is like heteroscedasticity. The standard error formula that we see all the time, for example, in simple regression, it's standard error of the slope in simple regression is sigma hat square root 1 x minus x bar squared. That formula that we've used many times to work out the standard error of the slope, which of course is then used to work out the t statistic and the confidence interval. This formula is based on theory that assumes 1, homoscedasticity, and 2, no serial correlation. As soon as you have either heteroscedasticity or serial correlation, then this formula is no longer correct. It's wrong. It's not a correct formula. So the point about this is, I think that this is probably the main problem with both heteroscedasticity and serial correlation. When you have these problems, the standard errors that we obtain when we use OLS are wrong, and that means the t-statistics are wrong and the confidence intervals are wrong as well. So this is the serious problem. But actually with serial correlation there's an even more serious problem, which is number 3. It may be that the presence of serial correlation is merely a symptom of a more serious problem. Consider the consumption function C, consumption depends on income and interest rate. Let's just assume that this is the true model which determines consumption. R is interest rate. Assume that instead of estimating 8, we estimate 9, which is C on Y without the interest rate. And obviously U is not the same as V, and that's why we need a different name for the error term in 9. The problem of serial correlation would appear to be present in 9. Why? Okay, the question here is this. This is the true model. This is the model that we estimate. And the difference is that in the estimated model, we do not have the interest rate. The interest rate appears in the true model. Why will the problem of serial correlation appear in the model that we estimate? Well, it's because look at the error term in the model that we estimate and ask what is the correspondence between the error term in the model and the true model? Well, everything up to here is the same in both models. So this error term Vt is the same as beta 3 RT plus UT in the true model. The error term in the model we estimate consists of 2 terms, one involving the interest rate and one involving the original error term. In other words, when you leave out a variable from a model, when you exclude a variable, that variable becomes part of the error term. The error term in 9 is essentially beta 3 RT plus UT. This error term must include RT because it's not in the model. It must be in the error term. So this is the important point. The error term includes the variable that's been excluded. Any pattern, and this is, so why do we get serial correlation? Any pattern in RT will be seen in VT, the error term in the model. Now, RT is the interest rate. The RT goes up and down. It has cycles. It has periods of low values and then periods of high values and then periods of low values. So RT is like other macroeconomic variables. It goes up and down in cycles. So if you leave out this variable from the model, the error term will go up and down in cycles because the error term contains this variable that goes up and down in cycles. Yes, VT is beta 3 RT plus UT, as I've written there. Yeah, error term in 9 is VT. Yeah, that's correct. Thanks. So this is why when you find serial correlation in a macroeconomic model, it's usually for this reason. It's usually because you've just left something out. There's something that should be there that is not there. And the pattern you see in the error term is just because of that excluded variable. However, this isn't serial correlation. This is a more serious problem. This is the problem of incorrect specification. Remember that there were 6 classical assumptions. The first of these, probably the most basic, is the assumption of correct specification. The model that you write down, which you intend to estimate, must be the true model. Well, if it's not the true model, then that's a violation of the assumption of correct specification, and that causes bias in your estimates. If you estimate the wrong model, then your estimates are biased. What are the effects of this problem? Bias in estimation. So, I've been telling you that heteroscedasticity and serial correlation are similar problems, but the way we deal with them is not really similar. With heteroscedasticity, it's easy. All you have to do is add the robust option, and that corrects the standard errors for whatever form the heteroscedasticity takes. When you have serial correlation, you want to think differently about it. You don't just want to correct for the problem. What you want to do is you want to get to the root of the problem. What is the reason for the serial correlation? And as I've been saying, it's usually because you've left an important variable out of the model. So you've got to consider, what have I left out? What can I include? Maybe which should be present, which is not there but should be. And you might find that when you include variables, now they might be completely new variables, or they might be lags of variables. So here we could use the lag of y, we could use the lag of r, or indeed we could use the lag of c as an explanatory variable. By adding variables to the model, you find that so often you reduce or eliminate the problem of serial correlation. And we'll see an example of that in the seminar workshop on Friday. That's page 63. Page 64 is what I will do tomorrow. The next lecture is 2 p.m. tomorrow. So I'll see you there. I'll stay around for a few minutes in case there are any questions, but I will